Hey guys, today we're going to talk about discrete random variables and their probabilities. So first, let's just review the difference between discrete variables and continuous variables. So if you remember from earlier this year, discrete data is data that can be counted or data that can take specific values, versus continuous data is data that can be measured. So we're going to focus on discrete data today, but just to kind of put this in perspective to what we're going to talk about more. If a cafe has 4 percolators, aka coffee machines, the number of percolators that fail on a given day is the quantity that changes randomly according to durability and reliability of the machinery. So you can count how many percolators are going to fail on any given day. Versus the weight of a coffee bag varies randomly according to the weighing and packaging process in the factory. So they're both random variables, but it's just one you can count and one is measured. All right, so we're going to use this terminology for random variables that are countable, aka discrete random variables. If we let X still represent the number of percolators failing on any given day, we would say X is a discrete random variable if these things are true. So discrete meaning it can be found by counting, random meaning it's a random process, and a variable meaning that in this case, X can take on any value in the domain of 0 to 4, including integers only. All right, so the first step in acquiring knowledge about X is to just create some kind of table. So these tables are going to look very similar. Your first row is going to be that domain that we had just talked about. How many numbers are you talking about? In this case, the number of percolators failing. We can have 0 that failed, 1 failed, et cetera, et cetera. Your second row is going to be the probability that each of those things happened. So the probability that 0 percolators failed, or the probability that 1 percolator failed. So what's nice about setting it up as a table is we know that these 5 probabilities in the second row must add up to 1, because if I have 4 percolators, something is happening here. Either 0 are failing all the way up to all 4 are failing. So these probabilities have to add up to 1, and each individual probability must be between 0 and 1 inclusive, because probability. Knowing these probabilities establishes the probability distribution of X, since the table shows how the entire probability of 1 is distributed to each value. So it's just nice because you can see all 5 options all at the same time. Kind of like setting up a tree diagram, but just in a table format. All right, so here's your official definition of a discrete probability distribution. And let's get into an example. So we have 2 fair die that are being thrown. One is a cubical die, meaning it has 6 sides and it's labeled 1 through 6. One is a tetrahedral die, which means it has 4 sides and it's labeled 1 through 4. The discrete random variable S is defined as the sum of the numbers on the 2 dice. So we're going to first construct a probability distribution of S as a table of values, and then find 3 different probabilities. So let's look at constructing that distribution first. So it says that the variable S is defined as the sum of the numbers on the 2 dice. So that means I could roll a 1 on the cubical die, I could roll a 1 on the tetrahedral die, so my sum would be a 2. Or I could roll a 2 on the cubical die and a 1 on the tetrahedral die, so my sum would be a 3, etc. So if you want to just think about it, that's fine. You can also create a table like I did, just to show the entire sample space. So we have all of these sums from 2 to 10 inclusive and only integers, since these dice only had integers on their faces. So now when I go to set up my probability distribution, I know my first row includes all the numbers from 2 to 10 inclusive. When I try to figure out my probabilities, I can see that the probability of getting a 2, well, there's only 1 out of all of these possibilities. There's only 1 2. There's a total of 24 possibilities, so that means the probability of getting a 2 would be 1 out of 24. I have 2 3s out of the 24, so that means my probability of getting a 3 is 2 out of 24, or 1/12, et cetera, et cetera. So it's the same probability that we've been doing for a while now. So if we use that to fill in the rest of the table, we should get something that looks like this. You don't have to simplify if you don't want to. We could have left these as the 4/24s that they are, or you could simplify all of them and simplify the 2 and 3s over 24 as well. It's your choice. But either way, that's our probability distribution. In part B, we're going to find these 3 different probabilities. So let's bring in our distribution table onto this slide just so we can have it visible to us. So first we're looking at the probability that the sum is strictly greater than 2. So some people last week were still asking about when's a good time to use the complement, or how do I know I'm supposed to use the complement? This is a perfect time to do so because we're looking at the probability of the sum being greater than 2. So I could, option 1, add up all of these probabilities, since those are all probabilities that are greater than 2, or all sums, that are greater than 2, and that works just fine. But on the contrast, I can just use the complement and say that the probability of getting greater than a 2 is just 1 minus the probability of getting a 2, since there's only one possible 2 that we're looking at. So it's just a good time to use it. You don't have to, ever. It's just sometimes a different option or a quicker option. Right, so that means the probability of getting greater than a 2 is 23 out of 24. Part 2, we're looking at the probability that the sum is at most a 6. At most 6 means 6 is the highest I can go. So it's the same thing as saying less than or equal to 6. So I'm looking at all 5 of these probabilities, or all 5 of these sums. Probability-wise, I'm going to add up all 5 of these probabilities, either using my calculator or using my head, either way, and I get 7/12. Finally, we have a conditional probability problem. We're looking at the probability that the sum is less than or equal to 6, like we just did, given that the probability is greater than 2. So thinking about the conditional probability formula, which again is in the formula booklet, it says that it's the probability of both of these, so this and that, divided by the probability of the given statement. So in this specific case, we're looking at the probability that the sum is less than or equal to 6 and greater than 2. So we're looking at these 4 values, divided by the probability that the sum is just greater than 2, which, great, because we already have that over here. So just to kind of tweak it a little bit, that might help in case you weren't sure why I was looking at these 5 pieces. We're looking at the probability that the sum is between 3 and 6 inclusive. If I'm greater than 2, strictly greater than, that means I'm including 3 and up. So that's why we changed it to a 3 and changed it to a less than or equal to sign. So I'm taking all 5 of these probabilities. Oops, sorry, not that far. Taking all 5 of these probabilities, 5, there's only 4. Taking all 4 of these probabilities, and adding all of them up for my numerator. And then my denominator is coming from part 1 that we had already done. So I have 13 out of 24 divided by that 23 out of 24, and simplifying, getting rid of those 24s in the denominators or keep change flipping, I'm looking at 13 out of 23 as my final probability. All right, so take a second to try this one. I know it looks different, but take a second to pause the video and see if you can figure out how to even get started on this. All right, so for this one, instead of giving us, a real world situation, they're giving us a function instead, where we have 2 different variables. We have the k, that if you read on, that's what we're being asked to find. And then we also have u, but they at least define u for us. They say u has to be part of the set of 4, 5, 6, and 7. So when I first start to create my table, I know that my numerator my numerator, my first row is 4, 5, 6, and 7. Sorry, I don't know if you can hear that. Coach Klein is doing some yard work today. My denominator, my second row of my table is coming from taking each of these values of u and subbing them into the function. So if I take 4 and I sub it in for u here and u here, I get 4k. If I take 5 and I sub it in, I get 6k, et cetera, et cetera. If you're not sure how I got those, again, take a second to pause and just do that substitution so that you can see where I'm getting those values from. So we had already said that all of these probabilities, every single time, no matter what distribution table you're looking at, they all have to add up to 1. So I'm going to take all 4 of those numbers, or values in this case, add them up so that I get 20k, and set that 20k equal to 1. So if I solve for k, that means k equals 1/20th, or 1 over 20. Final step, another substitution piece. I need to take that k equaling 120 and sub it in for each of the k's to figure out my actual probability. So for example, if I sub in 120 for k here, I have 4 times 1 over 20, which would just get me 1/5. If I sub in k here, 6 times 1/20th, which would get me 3/10. And I can do the same thing for u equaling 6 and the same thing for u equaling 7. So I hope that makes sense. If not, definitely try some of the practice problems before you go on to the check for understanding. And have a great day.